All right, so everybody, it's a pleasure to introduce Professor Jayakrishnan. Most people call him JK, so let's call him JK. JK graduated from Caltech how many years ago? 2010.
Rahul, there's some kind of echo.
Echo I can't control.
You need to be louder.
Can you hear me now? So some device must be logged in with a mic. That's the only way echo then gets generated.
Yeah, no, it's your voice is not clear.
Ah, that's okay. That's not the only thing not clear. Okay, so got a PhD from Caltech and then did a postdoc at CWI. And since then he has been at IIT Bombay. He also spent a semester, a few months here when Walker was around. Most people were not here. I was, and I think we know the world. The only people who were. And recently has written a very interesting book on heavy train distributions. If you're not checked it, what you're looking at. And without any further ado, let me pass it out to okay. I will care about online community more detection.
Thanks, Rahul. This is joint work with Meera Pai, who is a graduate student, soon to graduate graduate student in our department, and my colleague Nikhil Karamchandani. Okay. So let me get straight to the formulation that we are trying to solve. So the idea is as follows: you have a population consisting of 10 individuals. Okay. Now these individuals have been partitioned into k disjoint communities. So for this illustration, there is like a red community, a blue, and a green community. Right? 3 communities. The goal is very straightforward. Via sequential sampling of individuals in this population, the goal is to estimate the mode. Mode being the community with the largest number of individuals. So in this, you can see that there are more red individuals than there are green and blue. So red would be the mode of this. Right? Applications, let me just quickly go through a few. Election polling / post facto auditing. So in this case, communities would correspond to political parties, and the mode would then correspond to the winner of the election, right? The party with the largest number of votes. Opinion polling, same idea. Different communities could correspond to opinions. Mode becomes the most prevalent opinion. Very recently, these communities could correspond to virus strains, and then the mode becomes the most dominant strain, and so on. So the applications are very straightforward. So before I set up more, let me summarize. There are n individuals. These have been partitioned across k communities. Let's say the sizes of the communities are D1, D2, all the way through Dk. And sometimes, without loss of generality, we'll pretend that community 1 is the largest, just to keep the notation straight.
So you know k, and you know n.
Yeah. So here is exactly what we will assume. N is assumed to be a priori unknown. So I don't know the size of the population, but I do know the number of communities. These assumptions can be changed, and roughly the same methodology will work. But for the details to be precisely stated, these are the specific assumptions that we follow.
So in the streaming, so this is a streaming setting, right? So for example, in streaming setting, we know algorithms like, for example, let's say heavy hitters and something. So it is something similar to that.
I'll specify the algorithm.
Only what you have seen so far, but here it's also about the unseen.
Sorry.
So in the usual heavy hitter thing, it only is a sort of question about what you have seen.
What you have seen so far, yeah.
But here, I think you also are worried about what is unseen.
Okay.
There is a given population from which you're going to be sampling, and my goal is to estimate the mode which is a function of the entire population.
Heavy hitter.
Okay. So once again, the number of communities is known. The size of the population is a priori, right? So we will actually consider 2 different sampling models in this work. Both of these models involve sampling with replacement, right? So I pick up an individual from this population. I see something about that individual, put this person back, pick another individual next time around, and so on. And it's with replacement, so I can pick the same person multiple times. So the 2 different sampling models both involve with replacement, but they differ with respect to what information gets revealed to me, i.e. the learner, when a sample is actually collected. So we refer to this as identity-less and identity-based sampling, and I'll make this distinction precise in a bit.
This is the only way you can access the population?
This is the only way I can access the population. Right? So let me now tell you what the identity-less sampling model in this case is. So as the name suggests, in the identity-less model, all we assume is that you come to know which community this particular sampled individual belongs to, right? So for example, suppose I first pick that guy, so I see green, then I get a red individual, so my observation sequence is now red, another blue individual, then I happen to sample the same green guy that I saw before, but under identityless sampling, that is not revealed to me, so all I see is the sequence of colors, right? So if you give this a moment's thought, you will see that because of my fixed population, what I'm really doing in identityless sampling is getting IID observations from a certain discrete distribution. And so the problem of mode estimation in this case is just the task of estimating the mode from IID samples from a certain discrete distribution. Right? So it's a classical problem, people have studied it forever and so on. Right? So this is the identityless sampling baseline. Next, let me tell you what is identity-based sampling. In identity-based sampling, the learner is able to quote unquote recognize the individual that is being presented to it, right? So here is how this works. So again, I see the green individual, red, blue, and then this time when the green individual comes along, I actually know that I've seen this person before. So the whole idea of identity-based sampling is simply that when an individual is revealed to me, in addition to the individual's community, I also know whether I have seen this particular individual before or not. Right? So you can see that that next observation is marked with an R for repeat, right? And then this process continues.
So Jayakrishnan, if you were to do sampling without replacement, would the problem be much harder or would it be about the same?
It's different. I don't know. It's been studied. It's been, the problem has been solved in the without replacement work somewhat recently. I cited that paper by Wadby Smith and Aditya Ramdas from a few years back. It's a different problem. Let me just put it that way. I don't know if it's harder or easier.
Okay.
Yeah. Okay. So this is the observation model.
But even here, you do not know if there are 5 trees before, you do not know which one was this repeat. You just know it was somewhere.
Right. So this is a very, so even though we are calling it identity-based sampling, the identity information is very mild. So no Aadhaar number is being logged or anything of that sort. All I know is whether I've seen this person before or not. That's all. Okay.
Cookies.
Crucially, is there a question?
You're tracking cookies.
Yes. So the importantly note that the observation sequence is now no longer IID because repeats can happen and repeats will happen more often as time goes on and so on. So the observation process is non-stationary, specifically Markovian.
In particular, you do not know how many times you have seen it.
You don't even know how many times you have seen a particular individual before. All you know is that this is the repeat observation.
But this you can store. This information you can. So, but you get enough information to figure this out.
I get only enough information. So all I get is what I'm showing here. The color and a binary mark on whether you have seen this individual before or not. Then how many times I have seen this person before? Why did I see this person before?
Yeah, no, just
So I can't distinguish between two persons.
I cannot.
Yeah.
No.
So I can ignore this level and just go to the identity list.
Say that again?
I can just ignore this level.
Of course. So part of the point of this thing will be how much more you get by not ignoring this label, right? That is part of the story here.
It also is model where you have the cookie, like when you see the ID also. Right? That also makes sense.
Yeah. I'm sure. We haven't thought about that particular observation model. This particular observation model actually has been around for a while. People studied this way back in the context of cardinality estimation. So some of the applications that were put out, there are papers from the 70s that use this observation model for cardinality estimation of, say, different animal species in the jungle or something like that. So the idea is that you have a camera trap and you can tell whether this particular specimen has been seen before, but you don't store when, you only store seen before or not. Okay, so the observation sequence, the point to keep in mind at this point is that the observation sequence in identity-based sampling is not IID. That's important. Okay, so one of the questions that will come up is, in fact, how much of a performance bump, so far as the quality of mode estimation is concerned, would you actually get by exploiting this additional marginal, identity information? Okay. So in these kind of problems with, there are two flavors in which one can ask this question of estimation. One of them is what is called the fixed budget setting. Fixed budget setting is very straightforward. I get to see T samples or T such observations from the population. At the end of that, I or the algorithm has to announce that this is my estimated mode, and one is evaluated based on the accuracy of said estimation. Right. So the goal in the fixed budget setting would be to simply design algorithms, for example, with the minimal probability of error. So the probability that at the end of having seen T samples, I have misestimated the mode, that probability should be as small as possible. Okay, so this is a fixed budget setting, which is not going to be the primary interest of this talk, but I'm just setting it as a baseline, and I'll say something about this a bit later.
Now, Jayakrishnan, this fixed budget setting in the best term identification setting problems, it's known to be hard. What's the status in this setting? Is it known to be hard, or is it?
No, it's not. So I'll tell you. In fact, I'll run you through the main results. I'll flash them quickly, but it's not hard.
Okay.
Yeah. So next, this is the fixed confidence setting. The fixed confidence setting, in this case, the algorithm actually has to decide when to stop sampling. So after each sample is received, the algorithm now needs to decide whether to either continue to sampling or simply to stop and declare that this is my estimated mode, right? But it has to do this in a manner that actually satisfies a certain accuracy constraint. So specifically, there is an exogenously specified error threshold delta, and the algorithm should satisfy the following criteria. Suppose the algorithm stops at some random stopping time tau and gives the answer a hat, then the probability that I do stop and give the wrong answer is at most delta. Right? So delta, think of it as some sort of an error budget, which is exogenously and pre-specified to the algorithm. The algorithm must be designed in a manner that satisfies this. Probability that it stops and gives the wrong answer is at most delta. Okay? So algorithms that satisfy this condition are called sound or delta PC, where PC stands for probably correct. Was there a question?
So in this framework, would an algorithm stop and not give an answer, or
no?
So why say stop and give a? I mean, so this is.
So I have the option of never stopping.
Yeah.
So as such, being sound is not a big deal. An algorithm that basically does nothing, just will always sleep, is by default sound. Right, so it's soundless kind of like consistency, right? But just because your estimator is consistent, it doesn't mean that the estimator is good. So there's like a baseline requirement that one specifies. The goal is, it's clear that constructing a sound algorithm is trivial. A do-nothing algorithm is also sound. So the goal is to design sound algorithms with the minimal expected stopping time. So if you want your expected stopping time in particular to even be finite, you must stop with probability 1. In which case, it's really the probability of giving the wrong answer that is actually being counted, right? So in addition to being, so soundless is like a baseline requirement. And on top of that, we will say, I want to design sound algorithms which minimize the expected stopping time. Okay. So in some sense, it looks like the fixed budget and the fixed confidence setting are duals of one another, right? In the former, in the fixed budget setting, the budget is constrained and I evaluate the algorithm based on its accuracy. Here, in some sense, the accuracy is constrained and one evaluates the algorithm in some sense based on its budget, right? But yet it turns out that the flavor of algorithm design is very, very different between these two settings. It's not easy to translate algorithms that are designed for one to the other. Okay. All right. So to address Sandeep's question, let me give you a very quick express tour of the fixed budget setting. That's not the primary motivation of this talk, but it will already highlight and give some intuition for the utility associated with this identity information. Okay. So let me first talk about identity-less sampling in the fixed budget case, right? So all I get is a string of red, blue, and green, right? So the only reasonable thing to do is to really, at the end of it, output that community from which you have seen the maximum number of samples, right? This is the only reasonable algorithm to think of. And it turns out it's a straightforward application of the Chernoff bound to give you an upper bound on the probability of error of this algorithm. What I want to highlight here is that the probability of error decays exponentially with the number of samples I get with respect to the budget. This is
So Jackson, in this, there's no decision being made.
there
You're
is
just observing statistics. At the end, you're talking, okay, large deviation probability of making a mistake is so much and it has these bounds.
this case because the estimate is trivial. That's all there is. You're right.
Right. Okay.
Right. So the reason I'm pointing this out is simply that firstly, the probability of error decays exponentially with time. And in these fixed budget algorithms, therefore, the goal is to basically understand the rate of exponential decay. So that's this quantity out here. One basically wants to try and maximize this, right? So if you stare at, so it basically captures the rate at which the exponential rate at which the probability of error is decaying with increasing budget. It depends on the total population size, the size of the largest community, and the size of the second largest community. That is what dictates the decay rate associated with this algorithm. And it can also be easily shown that this is in fact the optimal algorithm. It should not be surprising.
So here the task, I got a bit confused. So task of the algorithm is to identify the community with the largest footprint.
Yeah.
That's all.
That's what we're calling the mode, the community.
That's how you define it.
That's all.
I thought you were supposed to estimate the probability, which of course you would do here.
We are not estimating. We just have to estimate the mode. In the fixed budget setting, you estimate the mode in the obvious manner, and what one cares about is what's the probability of error. The more interesting question will be later, where in the fixed confidence setting, you have to decide when to stop and announce something as the mode. That will come up in just a second.
But I guess this estimation problem looks interesting, right? If you had to estimate all the means after fixed number of samples, how to come up with kind of valid confidence intervals?
Estimate all the.
Suppose one had to estimate the means of each of these values, these probabilities.
So yeah. So people
together, that would be interesting, right?
That's very particular setting. I'm not. So cardinality estimation itself is imposed here because you're sampling with replacement with. So whether it's the same population or a scaled up version of the population, you can't really tell. But you could ask the question of estimating the fractions of each population, and people have done that before.
Right. I mean, it's like a probability distribution, finite support, and you're estimating all those values after having so many total number of samples.
Right. That's all. Yeah. So this is only to point out that this is the decay rate. It's quite easy to characterize, and this is in fact optimal. Now, what happens in the identity-based algorithm, right? It turns out that the correct algorithm in this case is to actually, at the end of T samples, output as your answer that community from which you have seen the largest number of distinct samples. Okay. Now, note that the observation model that we have assumed for identity-based sampling allows us to do this, right? Because whenever there's a repeat observation, I know it's tagged as repeat. So if I exclude that, the rest of the observations I have from that community are from distinct sightings of that particular community. So the right thing to do is in fact to output the community with the largest number of distinct observations thus far. Okay. So again, it turns out this is in fact the optimal thing to do. The probability of error in this case is again decaying exponentially with respect to the horizon. If one stares at the decay rate, again, it depends on the total size of the population, size of the largest community, and the size of the next largest community, right? What is interesting is that if you compare this decay rate for the identity-based case, it is in fact in general going to be much larger than the decay rate in the previous slide corresponding to the identity-less setting. In other words, the rate at which the probability of error decays is significantly faster for the identity-based setting than it is for the identity-less setting, which is another way of saying that, you can have, it is possible, it is significantly more accurate to identify you can have scenarios where basically the difference between these two correspond to sample paths where there was a different community that actually showed up the largest number of samples, but there was a different that actually showed you the largest number of distinct samples. So the algorithm that actually tracked the latter metric is actually more accurate than the algorithm that just went with the total count. Okay. So this already illustrates in a fixed budget setting that identity information makes mode estimation better. Any questions?
Is there an intuitive explanation of why this should be the case? I can see that it is at least as much because you can forget the identities, you have the original, but this loss of this change from square root to
I don't have intuition for that. You can, again, one can separately prove lower bounds and prove that these match lower bounds and so on. But I don't have intuition for the specific form of these two. Intuitively, identity-based sampling may, you kind of know when you are close to having sampled everybody, right? So you don't see when you start off, you don't see too many repetitions. After a certain while, once you've sampled nearly everybody or most of the population, the rate at which you actually get these repetitions grows. And there is information in that signature which can be captured, right? So
But,
that's my intuition for why this actually does better. Yes.
The prefactors, it's a pretty large, right? D1 choose D2. It was previously.
Because we don't care. So this is based on a coupon collector argument.
Right.
I have no reason to believe this is tight.
Okay.
This is just because we care about this, we don't really care about this. So this is based on a loose coupon collector argument, which fortunately for us identifies the decay rate correctly and optimally. The prefactor is way off. That's not of interest usually.
Yes, but let's say, I mean, in a practical scenario, what will happen? I mean, this D1 and D2. I mean, N has to be chosen in the order of D1 and D2, right? Or maybe some fraction of this.
Sure.
But if N is scaling in like this, then it is not clear like which one is. I mean, how good is this one? Assuming that this tree.
So this is the optimal algorithm that one can prove separately.
I see.
But as I said, the goal in this case is to basically maximize the rate at which the probability of error decays exponentially. That's the only goal.
Okay.
If you actually, set up a specific choice of N, D1, D2, T, and so on, this right-hand side may end up evaluating to be more than
I see.
one. That's not, this is not meant to be a numerically meaningful bound. The goal here is to simply be accurate with respect to this,
Okay.
which this probably is.
So Jayakrishnan, we are still in the fixed budget setting.
Yes, this is the. Yeah.
So total number of samples is fixed. In one case, if we see identity being repeated, we just ignore that basically.
Yes.
And then we announce the result, which is so. I mean, the two algorithms are kind of differing when the answers change.
Yes.
Right. I see. And somehow you're saying that this distinct individual algorithm is better in controlling the probability of error.
Yeah.
Okay, well, that's interesting.
I mean, if you just drop the repeats, is the marginal distribution the same as just picking without replacement? I mean, does it drop and it's not?
Okay, great. So now let's move on to the real point of the talk. We'll be specifically talking about the fixed confidence setting, where there is a confidence threshold that has been exogenously pre-specified. Our goal is to decide when to stop and flag a certain community as being the mode. Right? So let me start off with lower bounds in this case, which our algorithms will then seek to match. Right? Under identity-less sampling, here is a lower bound on the expected number of samples required by any sound algorithm, right? So you impose soundness. Those are the only algorithms that are interesting to us. And then we are saying that any algorithm requires at least on average these many samples. Okay. So there's nothing. So I'm not going to go into the proof of this because any of you who have seen, for example, lower bounds in stochastic bandits, the machinery is exactly the same. These are standard kind of change of measure based arguments. So there's nothing new here. So I'm going to basically just highlight the structural aspects of this lower bound itself. Thing to note here is that the lower bound scales as log of 1 by delta, right? So as delta becomes smaller, that means I want to be more and more accurate. Obviously, the lower bound goes up, but the manner in which it goes up is in fact of the order of log 1 by delta, right? This denominator here is basically what is specific to the underlying problem instance, okay? And here, P1 is simply the fraction of the total population corresponding to community 1. P2 is the fraction of the total population corresponding to community 2. So therefore, the lower bound essentially depends only on the fraction of the population corresponding to the top two communities. That is the point here. Now let me also tell you, so it is also quite easy if you stare at this, that this lower bound will actually blow up when P1 and P2 are close, in which case these two arguments in the KL divergence are actually close to each other. This is expected, right? So when P1 is close to P2, the underlying problem instance becomes harder. Any sound algorithm requires more time in order to estimate the mode to the specified accuracy. Right? If you do identity-based sampling, again, the corresponding lower bound is different. It has the same log 1 by delta type dependence on the error threshold. but the dependence of the instance is now different, right? And again, in this case, it turns out that the lower bound corresponding to identity-based sampling is in fact lower than the lower bound corresponding to identity-less sampling. And in particular, if you take the ratio of these two, that ratio goes to infinity as P2 approaches P1. So in other words, in the limit as my problem instance becomes harder, multiplicatively, identity-less sampling takes considerably more time as compared to identity-based sampling. Now, this again indicates that identity information is considerably useful, particularly when the problem instance is hard. However, mind you, these are just lower bounds. Once these lower bounds are achieved, only then is this claim actually realized, right? Because once I show that these bounds are actually achievable, then these bounds are actually tight, and so therefore they actually capture the true underlying instance of the true underlying hardness of these two problems.
So if P1 equal to P2, then the second one goes to infinity, right?
If P1 equals P2, the problem is not well posed because there has to be a unique mode, right? I want to estimate the mode.
Yeah, but this doesn't happen in the first case.
Oh,
I say so. It is just right. Okay.
Yeah, it does in both cases.
I see.
Right, so these are just lower bounds I'm stating upfront. The real interest is on the algorithm side, which I will spend more time on. So now let's talk about algorithms. Okay. Now, first I'm going to start off with identity-less and then subsequently go to identity-based sampling. Now, for simplicity throughout this discussion, I will pretend that there are just two communities. Okay, so there is community 1, which remember in identity-less sampling, as though I'm sampling from a distribution, the actual size of the population doesn't matter. Okay, so the problem instance is just parameterized by a single parameter P because I've assumed two communities. Community 1 has a fraction P of individuals, community 2, 1 minus P. So if P is more than half, then 1 is the answer, otherwise 2 will be answer. Okay. Problem instance is specified by this unique scale, simple scalar C, P. Sorry. Okay, so here is the observation model. Remember, I get this kind of an observation sequence, right? It is useful for subsequent characterizations to specify the likelihood function. So the likelihood function corresponding to the observations I have made up to a certain point, corresponding to a problem instance P prime. Remember, the problem instance is specified by a single parameter P, right? It's easily seen to be this. So the probability that I have seen these observations under instance P is in fact is going to be P prime raised to the number of samples I've seen from community 1 into 1 minus P prime raised to the number of samples from community 2. Okay. So before I move on to what we propose, let me go over one of the classical approaches that can be applied to this particular problem. So these approaches, these algorithm approaches are based on likelihood ratio, specifically generalized likelihood ratio statistics, right? So the classical GLR statistic applied to this problem goes as follows. So I have a hypothesis testing problem. There are two hypotheses, hypothesis 1, hypothesis 2, community 1, community 2, right? So a GLR statistic Z1 is basically capturing to what extent the data supports hypothesis 1 relative to hypothesis 2. So specifically defined as a log of the ratio of two likelihoods. The numerator here is essentially the maximum likelihood of the observations under hypothesis 1, namely that community 1 is in fact the mode. The denominator is the maximum likelihood over those instances where community 2 is in fact the mode. So this is the maximum likelihood under hypothesis 1. This is the maximum likelihood under hypothesis 2. The log of this ratio is what the statistic is, right? So yeah, so numerator is basically the maximum likelihood over this part of the instance, fix the denominator is maximum likelihood over this. So as you can imagine, if the true instance is in fact that the community 1 is larger, if your observations are such that you've seen many more samples from community 1 as compared to community 2, this maximum likelihood in the numerator is going to be much larger than the maximum likelihood in the denominator, in which case the Z1 becomes a large positive constant. Okay. So this is basically in some sense giving you some sort of a weight on to what extent the data supports hypothesis 1 versus hypothesis 2. Right? So how are these statistics used in order to decide when to stop? So you have obviously a similar statistic for Z2. So this is now community 2 versus community 1. Because I'm working only with two communities, in this case Z2 is just the negative of Z1. Right? That's all. And what is the classical GLR based stopping rule? It works as follows, right? I keep making these observations and computing Z1 and Z2. And there is a certain threshold beta. This beta, I'm not specifying the exact form here. It turns out it's of the order of log 1 by delta. Okay. So there's a pre-specified time varying threshold beta. And I stop sampling either when Z1 crosses this threshold beta or Z2 crosses beta. Okay. If Z1 is the one that crosses beta, I flag 1 as my answer. If Z2 crosses, then I call 2 my answer. This is my stopping rule. Okay. So I calculate these GLR statistics. At some point, if one of these statistics is to cross a certain time varying threshold, then I stop and flag the appropriate community as the mode. Right? So what can we say about this particular flavor of algorithm? It turns out that if this beta is suitably chosen, then one can show that this algorithm is in fact sound. So the probability that it gives the wrong answer is in fact at most delta. Okay.
Jayakrishnan, this problem seems to have enough structure that you can give non-asymptotic bounds too, right? Did you attempt that or?
Non-asymptotic in
E of tau is upper bounded by some for a given delta, not really for limit as delta goes to 0. Lower bound. Then some.
I'm not sure. At least all the arguments we have made tend to be asymptotic in nature.
Right. No. Reviewers won't like that, I can tell you that much.
Yeah.
There's a big demand for non-asymptotic analysis. Okay.
Right. So in addition, one can also prove that this approach is asymptotically optimal. What does it mean to say asymptotically optimal? You take the ratio of the expected stopping time under this algorithm to the information theoretic lower bound that we had identified before. The ratio of these, the limit of that goes to 0 along the asymptote where the error threshold is actually going to 0. So as delta goes to 0, right, my error allowance goes to 0. Note that the expected stopping time is scaling to infinity. So is my stopping time under this algorithm. This ratio will, however, go to 1. Right? In that sense, this particular stopping rule is known to be asymptotically optimal.
Do you also have a bound on the variance?
Not that I'm aware of. Not in this.
So it could be like a very largely variable, right? And the variance could be pretty large, even if in expectation it is optimal.
I'm not aware of the specific characterization of this, but it turns out that basically the way in which these algorithms are analyzed is that whichever is the winning Z, right?
Smarting
that will have a certain kind of fluid scaling as time goes to infinity.
Okay.
Now, if all you care about proving is asymptotic optimality, then I only care about the law of large numbers limit of this. But I suspect you can actually massage more out of it, which is going back to Sandeep's comment as well. What is going to happen? Suppose without loss of generality that community 1 is the winning community, then this Z1 will asymptotically grow linearly with respect to T. Now you can probably bound in some probabilistic sense how it is growing and come up with suitably non-asymptotic results as well. I'm sure it's been done. We did not.
I mean, in the bandit setting, the variance becomes a bigger issue because when things go wrong, you really undersample some arm. A good arm is being undersampled and you draw wrong conclusion and the variance blows up. My guess is it's much better behaved in this setting.
Because you're not sampling.
That's because you're not choosing. Yeah, you're just kind of sampling from two populations.
Yeah, so it's just an exogenous process whose
that's right.
The fluid limit has to be controlled. I'm guessing it can be done. We haven't.
So did you put this result in fluid limits? I thought that you just construct the Martin rules and.
No. So the way it works is that as delta goes to 0, your stopping time goes to infinity. That is easy to show.
Right.
So basically, all that matters so far as proving this result is concerned is what is the asymptotic growth rate of ZT. To be more precise, what is the asymptotic limit of Z1 T by T? Right.
I mean, the way this sequential SRPDJ works, so basically you construct a martingale, right, and get a bound by just using the martingale equal its expectation tau. There is no asymptotic, there's delta goes to 0.
This is an asymptotic. This is essentially a law of large numbers application.
Okay, I see. Okay.
So this is not a particularly difficult bound to prove, and this is so we haven't seen exactly this in the literature, but this machinery this machinery has been applied to bandits before, and it very readily applies to our setting as well. I'm only stating this as an easy baseline corresponding to how GLR statistics can be applied to this particular problem. Okay. So yeah, this can be done. What we actually propose is an adaptation of the GLR statistic. And this adaptation works as follows. Right? So remember, you have the statistic, which is the log of a maximum likelihood under hypothesis 1 to maximum likelihood under hypothesis 2. We modify this as follows. Right? We keep the denominator maximum likelihood under the competing hypothesis to be exactly the same. In the numerator, we replace the average, the max likelihood by a certain average likelihood. Okay, average likelihood of the observations I have made. Now, average with respect to what? You incorporate some fake prior, let's call it D, over the instance space. In this case, the instance space is just the unit interval. So I define some arbitrary density that has a full support over the unit interval, and I will average out the likelihood of the observations under the over the instances. Right? So the numerator is now you're replacing the maximum likelihood with an average likelihood over a fake prior.
I think I missed it. What are you trying to improve if the previous algorithm was asymptotically right? What is
Let me, yeah, that's part of the punchline. So it'll come out.
Okay.
Right. Okay, so this is what we propose. So now our rule is similar. I have W1 corresponding to this thing. There's a parallel W2, of course. And now I will again now stop either when W1 is greater than log 1 by delta or W2 is greater than log 1 by delta. In this case, because this is our proposal, I'm giving you an explicit description of what that threshold should be. Okay, so this is the algorithm. So we replace one of the maximum likelihoods by an average likelihood in the GLR statistic. And then we do the same thing, that you wait for one of these statistics to cross a certain threshold, and when it does, you flag the corresponding, you stop and you flag the corresponding community as the mode. Yes.
But now W2 is not minus W1, right?
W2 is no longer minus W1, indeed. Yes, good. Okay, so this is also, it satisfies all the same properties as the previous one, it turns out. And intuitively, the reason for this is actually not that hard to see. Because asymptotically, remember that the maximum likelihood will scale in a certain manner. Intuitively, you might expect that the likelihood is going to be maximum at the true instance value, and then it's going to plummet really fast elsewhere, right? So from an asymptotic scaling standpoint, basically the intuition is that this average likelihood is actually scaling at the same rate as the maximum likelihood. So that's the intuitive reason for why at least the asymptotic optimality works. The soundness argument, I'm actually going to give you the proof in just one slide from now.
So D is some beta distribution or something?
D doesn't matter what it is. It is some distribution whose support has to cover the entire instance space. That's all.
0 to 1.
In this case, 0 to 1. I mean, in general, in the multidimensional setting, it has to cover everything. And there are hacks around it. You can turn this into several 1 versus 1 type comparisons and so on. So there are, and later in the identity based setting, when we apply this, it's now not going to be just a unit interval, it will be a more complicated space. But
So
whatever the space of
the D, any such D is a complete support.
it should have complete support over the space of instances. That's it.
Okay.
That's all. That's the only
So
requirement.
Jayakrishnan, presumably in this setting, your adaptation won't help anything. It's just not harming very much. But you're saying in the identity setting, it's going to help? Is that the punchline?
Just, yeah. The punchline one slide from now.
Okay.
Yeah. So again, same guarantee.
The
it's
suspense
empirically-
is killing me. The suspense is killing me.
Yeah, but why not support it on half to 1? And because there you are taking max.
So a priori, I don't know, right? So I have to work on. No, I want the same. Whatever statistic I want the same thing here. There are variations of this that work, where for different statistics you give a different support and so on. But for
you
simplicity,
replace max, like there the max was over P dash from half to 1, right? So you would probably want to take prior on P dash to
doesn't matter is the point. Yeah. So you can make this a conditional expectation if you want, but you don't need it.
But
Okay.
why is the empirical performance better? I thought it'd be about the same or a little worse by doing this.
Why is it better?
Because the maximum guy will stop faster, right? You'll reach log 1 by delta faster.
Yeah, the reason it's better is actually because of the fact that for this particular strategy, the threshold I can choose in order to, while proving soundness, is actually better than the threshold you get for the other case.
And this idea generalizes then?
Yeah.
You do this in-
Yeah. So that's part of the punchline. So the point is, this is a much cleaner threshold. So you're not actually gaining with respect to the statistic, but because this statistic admits a much cleaner analysis, you can work with a much tighter threshold, and that's really the reason why the empirical.
No, but you can use this in the bandit setting as well.
We haven't done that yet. That's something that is currently being tried. Yes.
Okay, well, that's interesting.
Yeah. Okay, so same performance guarantee as before. So again, the question that many of you have been asking is, why bother, right? If you're getting the same guarantees, then why go through this adaptation in the first place?
Wait, before, did you say that it's easier to analyze and therefore you use this?
For this simple setting, both of these statistics are very, very easily computable in closed form.
No, but the ease of analysis should not affect the empirical performance, right? It doesn't matter whether you can analyze it or not.
Yeah, but because of the analysis being, well, I shouldn't say easy analysis, but tighter analysis here allows you to use a tighter threshold here. That's the point. That's the reason why the empirical performance is better. You get the same, whether you use log t by delta or log t square by delta, all of these things probably give you the same asymptotic performance. But the point is, empirically, the fact that you had to use a worse threshold here to make your proof work for the statistic.
But why do I need to make the proof work if I'm doing empirical analysis?
No, you're doing empirical analysis on a sound algorithm, right? To prove soundness, you need to set the threshold to whatever it is. But now I have two algorithms which are both sound. Which means asymptotically, they are kind of, the ratio of the stopping times is 1, but that doesn't stop one of them from empirically being better than the other in the breeding.
Right? But Jayakrishnan, this old W1T was strictly dominating your new W1T, right? So whichever way you come up with the threshold, one should still be, the first one should still be faster than the second one.
No. So I'll show you why. Just
okay, yeah, because that's not, yeah.
Okay, so the way I will illustrate this and to also make the point of why bother with all of this adaptation is to basically run you through the proof of the soundness of this stopping group. Okay, so that's it. It's a small enough proof that actually I can go through this in the talk. So here is the proof of the soundness of our policy. In other words, for this stopping rule, the probability that you make a mistake is at most delta. This is the proof of that statement. Okay. So again, we are working in the simple two community type setting without loss of generality. Suppose that the underlying instance has community 1 being the largest community. So P is greater than half. Okay. So the probability that you make a mistake is the probability that the algorithm outputs 2 instead of 1. Now, what is the probability of this? This is the probability of corresponding to all of those sample paths of observations, which would result in our algorithm giving the wrong answer. So this is just for concreteness. I've read some time from 1 to infinity, and these are t-length sample paths, which would result in the algorithm stopping and giving 2 as the answer. Right? This total likelihood is a probability of that. Now, this can be trivially upper bounded as follows, because I've assumed that my instance has p greater than half. I can upper bound this likelihood by the maximum likelihood over p prime greater than half of the observations contained within this set. Agreed? So now all we do is multiply and divide by the expected likelihood over my fake prior d.
So 2 is p is greater than half.
Yeah.
But you're making a mistake. So the likelihood should have appeared larger when p was less than half. That's how you make the mistake.
No, you make a mistake when the statistic corresponding to 2 fires.
Correct.
In the statistic corresponding to 2, the wrong answer, so to speak,
Right, so
corresponds to p greater than half, right?
Yeah, but then it should not be less than equal to prime greater than.
No, the actual p is greater than half, right? So all I've done is basically multiplied and divided by this. Now this is basically just the reciprocal. Well, the log of the reciprocal of this is in fact the stopping w corresponding to the wrong answer 2, which fired, right, and caused my condition to get triggered, which tells you that this quantity is actually at most delta from the stopping criteria itself. Okay, so that delta now comes out and you end up with this. Now, if you stare at this, what is this? This is the sum over a whole bunch of sample paths of the expected likelihood of the observation sequence where this expectation is over a distribution of instances D. D is some fake prior over the instance space. So what is the trivial upper bound on this double summation? I mean, I told you that the probability of error is at most delta, so the upper bound is going to be 1. But if you stare at this summation for a bit, what you will see is that this is simply the probability that when the instance is drawn randomly from my fake prior D, my algorithm stops and actually gives 2 as the answer. That is this probability. That probability is what this double summation actually corresponds to. Okay, so therefore, being a probability that is 1, and so therefore the probability of error is at most delta. That completes the argument. Right? 4 lines of argument, and it turns out that this step is actually what is much harder to justify and work around when you work with the classical GLR statistic as opposed to our modification. Because I have an expectation with respect to a fake prior, this entire thing is basically bounded by 1 because this is just a probability distribution over the space of over the observation space. And that is what gives me this upper bound. In the other GLR statistic, what I would have to multiply and divide by is a certain maximum likelihood. The maximum likelihood does not define a probability distribution over the observation space. And so now you have to multiplicatively kind of bound this by some suitably large constant, which then has to be baked into my beta threshold to compensate for, right? That is the reason why you need a more conservative stopping threshold for the conventional GLR statistic, right? And not to mention, if you look at the proof of this, if you look at this is the 4-line proof, right? The corresponding proof for the GLR statistic is actually the original GLR statistic is much longer and much more complicated, primarily because I have to justify this suitably, right? One has to invoke some result from information theory that bounds likelihoods in terms of densities and so on, and somehow come up with a bound. This becomes much simpler. Okay. So what I have now given you is a 4-line proof for why the algorithm that we propose is in fact sound. Now, can somebody from the audience venture a guess on why it is that we bother with defining this new modified GLR stopping rule in the first place?
Better empirical.
No, that is a post facto, happy coincidence. But why, from an analytical standpoint, there is one, a shorter proof is not the answer. But
why you've got the ratio you're now bounding by, I guess, log 1 by delta, right? So it becomes.
You get a better threshold that gives you better empirical. Yes, but there's something much stronger.
Identity thing is probably easier to analyze. The identity.
So the main reason why this is useful is because at no point has one made any use of the IID nature of the observation sequence. Right? So the observation sequence could be some arbitrary non-stationary process, and absolutely nothing about this 4-line proof changes. If you
your distribution D is kind of, it seems to be, it's true for all distributions D. Is that right?
Not just D. The point is that in this case, it turns out that the observations were IID, but nowhere in this proof is that actually exploited.
No, it is. When you say it is L subscript P, it means there is one parameter P, which means it is that.
No, but it could be.
Then if you are explaining over an arbitrary. The point is the space will change, but the proof doesn't change. It's basically the same proof would work in a non-IID setting as it does in an IID setting.
So in the other proof, some law of large numbers things have to come up at the.
There is some distribution-specific concentration inequalities that you require to make the classical. So if the classical GLR proof, even in the IID case, would be much longer and would take much more work. If you now wanted to translate that to some Markovian setting, for example, the old concentration bounds wouldn't work, right? This part of the bound, now you have to come up with some other custom, inequalities and bake whatever compensation you have into the beta and all of that, right? All of that becomes much more complicated. Now you have a one-size-fits-all kind of solution. Even though I'm illustrating this for the IID, observation setting, this is extremely general, right? So all you have done is basically killed one of the maximum likelihoods and replaced it with an expected, likelihood in your GLR statistic. And now suddenly your statistic becomes, significantly more generalized.
So how does D affect the bound, the distribution? I mean, it has to come into picture somewhere, right?
Only empirically. See, at least in the, yeah, it does, of course it does. So the point, we can talk about that. Yeah, it will dictate in an asymptotic regime, it will not affect, but in practice, because the expected likelihood is computed over D, if D is to put more mass around the true instance,
Yes.
obviously that will improve performance.
Right.
If D is really pessimal and puts more mass elsewhere, then that would degrade performance. None of this
So in a
plays a role in the
million,
asymptotic limit,
right.
but indeed in the pre-limit, how you choose D. If you have some, hunch about which community is larger,
Right.
you could design your D such that you put more probability mass there. So it gives you the benefit when you're right, but it's robust to you having been wrong.
So since the original thing was optimal, essentially D has to be such that the saddle point, the point that the mean looks like the mode does not actually go away.
Yes.
And so that's the point. And then
That's the only point. Indeed. Oh,
and that's the IID thing. I mean, for that, something like concentration or IID would be needed.
so for which?
For this, like because you have to do this argument again. I mean, somehow the performance has to now go back to the classical one for the time restricted time analysis.
No, it turns out you don't need to work that. It actually, I mean, the intuition is indeed what you're saying it is, namely that the point where the likelihood is maximum actually will correspond to the true instance, and the maximum likelihood is in fact, maximum there and plummets really fast. So the average likelihood, the scaling of the average likelihood is going to be the same. That's the intuition for why it happens, but it turns out for the asymptotic analysis, we don't have to actually run that.
But can you adaptively change your D in T?
We didn't try. Actually, I
I
mean,
mean,
be surprised if this proof will just go
this
I
through.
mean, the last line, right? You have to justify again.
One is to justify, yeah, this overall time. So one is to justify this D is to be chosen adaptively in some manner, then, I mean, if it is a non-adaptive function of time, I'm sure it works. If it's adaptive, one probably has to work a
Because
bit
all
harder.
these terms have to go inside the expectation
Yeah.
to make it a problem.
Yeah.
Here, I think this put the expectation out, and which is basically, yeah. Anyway,
I mean,
so
if your D was fully masked on the best solution, then that you're back to the old setting, and that it obviously doesn't work, right?
indeed, right? So the key point, as I mentioned here, is that the proof makes no reference to the data being IID. It's the same 4-line proof, basically will prove soundness in any type of non-stationary setting as well. Okay. Okay, so with that, let me get to the identity-based setting. Now, here
So what Sandeep just said was about this P being, but actually that is probably the best algorithm it cannot be implemented, right? So he was saying that if D was supported on the best P, right? So that of course we don't know, but if we knew that, then the GLR thing, so there's been no max level, just that one likelihood. And that's probably the best algorithm in some sense, but it of course not implemented. Is that right? Yeah.
So there is as such, no.
So the analysis will work even for that, but it's just that it's not an implementable.
It's not implemented. But
I was thinking more on the empirical best.
Over time.
Yeah, so there is, so at least in the identity based setting, we will do some adaptation of this around those lines, which I will mention in a bit. But at least actually, I hope it's also clear that the story with the identity based case is now going to be fairly straightforward. Our lower bounds already tell you why identity based sampling is superior to. So if you're able to match the lower bound, then you're going to get the full benefit that the lower bound suggested. And the machinery that I told you, I mean, it now is very nicely amenable to the Markovian observation structure that is induced by the identity-based setting as well. Okay.
But you've not shown us, first of all, a better threshold, and second, empirical results in this setting. You're saying that they're better.
Empirical results are in the paper. I haven't put them here. The better threshold is, in fact, this log 1 by delta is in fact better. It doesn't even scale with T. If you look at the results that you get on the classical GLR statistic, that delta threshold has to grow with T.
I see.
Yes.
So in this case, it's log 1 by delta, which is a smaller threshold, but then you're using a weaker kind of stopping, your likelihood ratio function is smaller also. But
Yes.
in balance, you're saying that empirical works out.
Exactly. That I cannot justify analytically, but
That's right. Yeah, it'd be nice to see.
That's very interesting because like you assume some kind of random walk happening in the log statistic and usually the idea that it should cross some threshold. The threshold should usually in most random walk setups be growing with time. Like, some kind of root.
we just went through the proof of
Yeah,
summons.
that's right. Right, that's it.
Okay, great. So now identity-based setting. So in the identity-based setting, the size of the population matters. So my instance space is a bit more complicated. Again, for simplicity, I'll pretend that I'm working with two communities. So let's pretend that there are D1 individuals in community 1, D2 individuals in community 2. Earlier, my instance was specified, by a number in the unit interval. Now my problem instance is specified by a pair of natural numbers. Okay, so it's now an infinite instance space that one has to work with in this setting. Okay, so now my observation sequence, remember, was that I see the color of the, of the individual, but I also know whether I've seen this person before or not, right? One can define a GLR statistic analogous to what we did before. Define some fake prior D over now my two-dimensional, non-negative integers space of instances. Numerator is basically average likelihood of the observations averaged over that fake prior. The denominator is now the maximum likelihood over the competing hypothesis. Okay, same thing as before. It turns out that exactly the same analysis, the same 4-line argument as before, shows that this is in fact sound, right? And an analogous argument as before actually shows that this is also asymptotically optimal, right? So you would think the story is, is done. But there is one issue, there's a catch here, which does not arise in the identity-less setting. And the catch is that this particular algorithm is computationally intractable because this particular object, both the numerator and the denominator, are a pain to calculate. Right? Let's look at the numerator. The numerator is just, this is a double infinite series over my non-negative, this thing. This is not going to have, this is not going to have a meaningful closed form, for any reasonable prior then. Think of what is worse is actually the denominator. If you look at the denominator, I'm asking you to maximize this particular likelihood function over a discrete infinite set. Right? Again, one can do something because I know that eventually the likelihoods will start falling off, and one can probably come up with some sort of truncation argument to make it more efficient. But this is also quite painful to do, and I have to do that every time. Right? So that is the reason why the stopping rule, exactly as is computationally, it works. It will give you the same asymptotic performance guarantees and so on. However, this is not computationally tractable. Right? So what we have done for this particular thing is to basically come up with a further relaxation of this statistic, which basically preserves both the soundness as well as the asymptotic optimality of this original intractable one. Okay. So I'm just going to quickly highlight what those adaptations are. The details don't have any specific insights, so I'm not going to go through them. Right? So here is the original GLR statistic, the modified GLR statistic that we began with. Now, in terms of the numerator, what we will do is replace that expectation by, so the expectation is a double sum over the space of all non-negative integers. I will basically take only a certain number of terms in that double summation. Specifically, I can just take a single term corresponding to the vector corresponding to the number of distinct samples of community 1, number of distinct samples of community 2. There is one entry in this double summation corresponding to this value. I will only take that one number in my numerator and nothing else. Okay, so only one term of all the terms in the numerator expectation computation, only one term I will include. That now becomes tractable, it's a lower bound. So what we are going to do, this relaxation is going to basically produce a lower bound of my original statistic. Okay. Now, why is this reasonable? Because eventually, this is going to approach the true sizes, the likelihood is going to be maximized here, and so this is enough to capture the asymptotic scaling of my likelihood, right? Even though in the pre-limit, as Sandeep has pointed out, you are actually, I'm further lowering my statistic for computational tractability, right? In general, you can take some ball around this vector, and that will give you slightly better empirical performance. So far as the denominator is concerned, what we are able to do is take this discrete optimization. This likelihood function gives you a nice clean extension over the non-negative reals and solve that non-negative real over that optimization over the non-negative reals rather than over the integers. It turns out that that can be done tractability even in the K community setting. We can basically solve that optimization tractably using the specific structure of the likelihood function that is available in this particular case. Right? So the numerator, I just take a single term. The denominator, we can actually tractably reduce this to a 1D problem, right? Which is now going to give me a maximum likelihood over a continuous extension of the originally discrete space. So it's going to give me a larger optimum value and therefore a slightly smaller value of the statistic as well. Right? So the main contribution is to show that in spite of doing these two relaxations in the benefit of tractability, you still get the same asymptotic scaling, you still get the same soundness guarantees as well. Okay, so that is the main takeaway so far as the identity-based setting is concerned. So that brings me essentially to the end of this talk. So we talked about this fixed confidence mode estimation problem. We showed basically that this very simple I have seen you before type identity information can significantly improve the performance of your mode estimation algorithm. And the main, shall we say, novel contribution from our side is really this modified GLR statistic, which basically gives you better empirical performance. But in my opinion, the main benefit is the fact that you are able to now generalize this far more easily than the classical GLR statistic, for which the soundness argument and the threshold has to be customized for the specific stochastic observation process that one is actually dealing with. Right? So this is now general, arbitrary, non-stationary type models can be handled. Right? In the paper, if you're interested, you can find a bunch of numerical case studies where this bump is actually illustrated. How do you go from 2 communities to K communities? If there are questions, I'm happy to answer, but that is also somewhat straightforward that we talk about in the paper. And the details of this relaxation and how we are able to show that it still continues to give the relevant guarantees, that can also be found in the paper. So I'm happy to take questions, but that's
So you're able to do what's called even an arbitrary stationary process. So that
non-stationary, yeah. Like the Markovian, we applied this subsequently to a specific Markovian problem.
Okay.
The identity-based structure is a very specific Markovian structure, but it doesn't have to be that Markovian, it should be anything.
I mean, any arbitrary stationary process will be fine.
Non-stationary works, right?
Non-stationary. Non-stationary, why non-stationary?
So, for example, the observation process in the identity-based setting is non-stationary. It's like
the way the data is actually generated. Let's say in the identity-less setting, right? So let's say, I mean,
then it's just IID, no?
The identity setting.
In the identity-based setting, as time goes on, you will see more and more, repeats, right? So it's a non-stationary Markovian.
You don't see it.
okay.
At some point, so it's basically an absorbing Markov chain,
Right.
which describes the observation.
So in the identity-less setting, it's still IID.
Yes, but the machinery is more general.
So I was thinking of the situation. So let's say this is an identity-less setting, but instead of being IID, you're getting observation from some stationary process. Maybe this is a Markovian process. Okay. Does the loop go through in that setting? Because if you're just computing likelihood, right? And let's say
the complexity is in the computation and the optimization of those likelihoods. That's the computing the statistic is the hard thing. That the statistic is sound with the same argument that I've given.
Right. And I was thinking about this situation. So suppose, okay, so now if it goes through like for any stationary process, because you're not particularly taking advantage of the IIT nature, the likelihood computation. So let's say I can compute the likelihood.
No, the likelihood computation of course exploits IID-ness.
But if it's a Markov chain, you can probably still do something similar.
Which is what we do. In the identity-based setting, there is so I know what the transition kernels are, but I think the real power is the fact that this particular type of GLR statistic, soundness can be proved in very, very general settings. The bottleneck will be the computation of that statistic, where you may have to make due relaxations as we do, depending on the specific.
So if you have an oracle that can compute the likelihood, then and for any arbitrary stationary process, then the thing goes wrong. So this was my question.
So maybe one question around that would be like if the community was on a graph and we could only like after sampling one person sample a neighbor, right? Then if the graph is expanding enough, it should probably work.
I suspect.
But the dependence upon the expansion is probably not going to show up here because it's going to be eaten up by the other things possible.
It is, I mean, I suspect it will play into the complexity of computing these.
But it will probably go into some constant terms and like when you take
That I'm not sure.
It's just probably just so the question is basically the question is just can this algorithm take advantage of the actual mixing rate or does it just depend upon the fact that the chain has some mixing? So basically can it detect is it sensitive enough to give different answers based on how quickly
Good question.
the random was moving
I don't know.
on the mixing?
All right, any more questions? Yes, thanks, speaker again.
Short post is.